Hello and welcome. You ever stop and think about how we can send these massive files, photos, and videos across the internet in just a few seconds? Well, a huge piece of that puzzle is something called data compression. And today, we're going to pull back the curtain on one of the cleverest methods out there, Huffman coding. Let's get right into it.
So, let's kick things off with a simple but really important question. Think about the English language. We use the letter E all the time, right? But how often do you use the letter Z? Not so much. So why on earth should they both take up the exact same amount of space inside a computer file? It feels wrong, kind of wasteful, doesn't it? Well, that's precisely the problem Huffman Coding was designed to fix.
You see, the old way was kind of like a one-size-fits-all t-shirt. It technically works for everyone, but it doesn't really fit anyone particularly well. Every single character got the same fixed amount of space, let's say 8 bits. Simple, yeah, but not very smart. The smart way, the Huffman way, is more like getting a tailored suit. It's a custom-fit system where the characters we use constantly get these tiny, efficient codes, while the ones that rarely show up get longer ones. It is all about being smart with our space.
So, let's put a formal definition on this. Huffman coding is what we call a greedy algorithm. Now, I know what you're thinking. Greedy sounds bad, right? But in the world of computer science, it's actually a compliment. It just means the algorithm is incredibly focused. At every single step, it makes the best possible choice right now to get to the best overall result. For us, that goal is the smallest file size possible.
Okay, this is probably the best analogy for Huffman coding, period. Think about it. Your best friend Christopher, who you see all the time, you probably just call him Chris. It's short, it's fast, but that guy you met once named Montgomery, you're probably going to use his full name. Huffman coding does the exact same thing with data. The most common letters get short, easy nicknames. It's really that simple. All right, enough theory, right? Let's get our hands dirty and see how this actually works. To build this thing, we need a blueprint. And our blueprint starts with a simple step. We just need to count up our characters. So let's say we scanned a bunch of text, and this is what we found. You can see right away it is not even close to being balanced. The letter F is our superstar here, showing up 45 times, and way down at the bottom, poor A only makes an appearance 5 times. This lopsidedness, this imbalance, that's the exact thing Huffman coding is designed to exploit. All right, now for the really cool part. We're going to take these numbers and build something called a Huffman tree. And I want you to think of this like a construction project. We're going to start from the ground up with the smallest, most humble pieces and build our way to the top.
Every good construction project needs a solid foundation. For us, that means we look at our list and find the 2 characters that show up the least. In this case, that's A with a frequency of 5 and B with a frequency of 9. We're going to take those 2 and combine them into a new parent node. Add them up. 5 plus 9 is 14. Boom! First step is done.
Okay, let's keep building. The process is exactly the same, which is what's so elegant about this. We look at what's left and find the next 2 smallest frequencies. That's C with 12 and D with 13. We'll merge them together into their own little family. 12 plus 13 gives us a new node with a combined weight of 25.
Now, this is the really important part, so watch this. We repeat the process, find the 2 smallest things in our list, but this time it's not just single letters. The smallest things we have are that new node we just made, the one with a value of 14, and the character E with a value of 16. So we combine those. 14 plus 16 gets us a new, bigger node with a value of 30. See that? We're starting to build with the blocks we've already created.
We are getting really close now. Let's take stock of what's on our construction site. We've got the node that's worth 25, the node worth 30, and our most frequent character, F, all the way up at 45. The rule is still the same. It never changes. Find the 2 smallest. That's 25 and 30. Let's merge them. And boom, we get a new, even bigger node with a value of 55. And here we are, the final piece of the puzzle. We only have 2 things left, our superstar character F with its frequency of 45 and our massive combined node worth 55. You know the drill, we combine them one last time. 45 plus 55 gives us 100. And hey, if you add up all our original frequencies, guess what you get? 100. It all comes together perfectly. Our tree is complete. Okay, so we just spent all this time building this thing, this tree. You might be asking, so what? What was the point of all that? Well, this is the payoff. This is where all that work gives us something incredibly valuable. Let's see the new, super efficient codes we've just created. Reading the codes from this tree is actually super easy. There's just one simple rule. Anytime we travel down a branch to the left, we assign it a 0. Anytime we go right, we assign it a 1. That's it. So to get the new code for any character, we just start at the very top, the root, and trace the path of 0s and 1s all the way down to it.
And here it is. This is the magic. Just look at F. Remember how common it was? Its new code is just 0. That's one single bit, instead of the usual 8 bits it might have taken before. That's a massive saving, and it happens 45 times. And on the flip side, look at our rarest letters, A and B. They're buried deep down in the tree, so they get the longest codes. This is what it's all about. This is smart, variable length coding.
And this chart really just drives the point home. High frequency, short code. Low frequency, long code. It's an inverse relationship. The huge savings we get from our superstar letter F far outweigh the tiny extra cost of the rare letter A. And when you add it all up across an entire file, the result is a much, much smaller file. So, you might be wondering, how do we know this is the best way? Why does this simple, greedy method give us the absolute best compression? Well, it's because of something computer scientists call the greedy choice property. It basically proves that by always making the best local choice, just grabbing the two smallest things, we actually end up with the best possible tree overall. It's pretty amazing. Let's give this algorithm a report card. In the world of computer science, we don't just say an algorithm is good or bad. We have an official grading system called algorithmic complexity. It's like a performance review that tells us exactly how fast and efficient an algorithm is, especially when the amount of data starts getting really, really big. And Huffman Coding's official grade? It gets an O of n log n, which is basically an A+. You don't need to worry about the math. All it means is that this thing is incredibly efficient. As files get gigantic, it doesn't just grind to a halt. It scales beautifully. That's why it's a foundational part of what we call lossless compression, where no data is lost. And it's working behind the scenes in so many things you use every single day. We're talking zip files, JPEG and PNG images, MP3s, the list goes on. So yeah, from the zip files you download to the photos you share, this brilliant little nickname system is working silently in the background, making our digital lives faster and more efficient. So now that you know how it works, think about it. Where else in your digital life do you think a system like this is saving you space without you even realizing it? Thanks for joining me.